Beginning of my chapter Kaplan Mcat chapter reviews. We'll begin with my current unit in physics of chapter 5, electrostatics and magnetism. We'll begin with the introduction. Electrostatics is the study of stationary charges and forces that are created by and which act upon these charges. So electrostatics is the study of stationary charges and the forces it acts upon and our electrostatics is the stationary charges and specifically the forces it acts upon and are created by these charges. That is very important. Without electrical charges, we would not be able to do many of the activities we enjoy doing. That we enjoy or consider essential to basic living. Without electric charge, we will not be able to enjoy activities we consider important to basic living. But living with electrical charge can even be deadly. For example, it could be deadly in this sense. So we basically it's saying that we need charges to live, but it can be deadly. And so we, in medical purposes, it seems it can be used for life-saving purposes. For example, it could be used for life-saving purposes that include what? Life-saving purposes that include what we call cardioversion, but also deburlifiers can also be used for deburlifiers. So what we learned so far, electrostatics are important to for life-saving purposes. These are important for life-saving purposes, but can also cause deadly harm. But it could be used in cases where you need cardioversion or debrylation. But also note that it's more about stationary charges and the forces that acts upon and is created by these charges, stationary charges. In this chapter, we will review the basic concepts essential to understanding charges and electrostatic forces, including conductors and insulators. The charges and electrostatic forces. Essential, basic concepts essential to understanding. We will learn about basic concepts essential to understanding charges and electrostatic forces. Basic concepts essential to understanding charges and electrostatic forces. By that, what do they mean? We will learn about basic concepts to understand. We will review basic concepts essential to understanding charges and electrostatic forces. So when we will learn about conductors and insulators. We learn about conductors and insulators. We will review Coulomb's law. Which describes we will learn about Coulomb's law that describes the attraction or repulsion of two electric charges. Next, we will describe the electric fields that all charges create. And so, yeah, that's important. We need to know that charges create electric fields. I think this is quite important. Charges create electric fields. That's important. Next, we will describe electric fields that all charges create. Which allow them to exert forces on other charges. Hence, these allow to impose. Electric fields allow us to impose forces on other charges. Interesting. Next, we will discuss how charges set up fields. We'll observe the behavior. We'll observe the behavior of charges that are placed into these fields. I see. And so we'll observe this, and then what we'll do is we'll observe behavior of charges within electric fields. This is quite important. Particularly, we will note in particular, we will note the emotional behavior of these charges inside a field in relation to the electric potential difference. So, in particular, we will note the emotional behavior of these test charges inside the field in relation to the electric potential difference. Observe evidence. So we'll find how this relates to electric potential difference. That's quite important. Also known as voltage. This is also known as voltage. So we know charges create electric fields, and the electric fields are created for the purpose of exerting forces on other charges. And by imposing forces on other charges using the creation of electric fields from source charges, we can observe the behavior of charges within electric fields, and we will see how this all relates down to electric potential, which is also known as voltage, between 2 points in space. Then we can determine the change in electric potential energy as the charge moves from position of some electric potential to another. And we can use this to explore what it says. You can determine the change in electric potential. So, we can determine electric potential energy as we move. What do we move? As we move a charge, we could determine electric potential energy as we move a charge from one electric potential to another. Next, we will describe electric dipole and solve a problem involving one of the molecular dipoles, most important. Life on planet, water molecule. And so from this, we could determine the electric potential energy as we move from charge from one electric potential to another. Change it. Next, we describe the electric dipole. Solve a problem involving one of the molecular dipoles, most important to life on planet. Next, we will then learn about electric dipoles and specifically on water. And we'll tie all of this in finally we'll explore topics of magnetic fields and forces. Tie all into magnetic fields and forces. Now that we got this out of the way, we could get into 5.1. We shall get into 5.1. 5.1 says what? Oh, we are learning about charges. Learning objectives. Contrast the behavior of protons and electrons. So learning objectives for one, to categorize materials, including glass and copper, as conductors or insulators. 3. Recognize the charge of an electron in coulombs. Okay, so learning objectives 1, we will learn about the behavior of electrons versus protons. 2, we shall do what? 2, we shall do what? 2, we shall learn about define insulators versus conductors. Define insulators versus conductors. And 3, we shall do what? Define charges in coulombs. That's what we're doing. To tie it back in, introduction is this chapter is about electrostatics and how it's basically about what is it? Electrostatics is about the stationary charges and the forces it acts upon, and the forces it creates by these charges. That's the definition of electrostatics. And basically we need electrons to live, but they can be deadly. We need charges to live, but they can be deadly. We need electric charges, but they can be deadly. And so for life-saving purposes, electrostatics and just charges in the field of electrostatics, it can be used in cardioversion, and also in deep relief fission, which are medical purposes. Now, they could serve life-saving purposes, but can be deadly, as we learned. These can serve life-saving purposes, but can be deadly. And then we could learn about conductors and insulators, the difference between the two. And we're going to learn about Coulomb's law. Coulomb's law is basically way to describe the force exerted upon two forces of charges. So source charges create electric fields, and those electric fields are a way to engage in force activities with impose a force on other electric charges. And we're going to observe behaviors of charges within those electric fields, and we're going to relate it to electric potential energy difference, which is known as voltage. Voltage is electric potential energy difference. From there, we will determine electric potential energy as we move charge from one electric potential to another. And we will learn about electric dipoles, and specifically on water, and tie this all into magnetic fields and forces. Learning objective 5.1. Interesting. Charged subatomic particles come in two varieties. One is positive charge and the other negative. Opposite charge, like charges that have the same magnetic repulse. Unlike forces of gravity, which is always an attractive force, electrostatic force may be repulsive, may be attractive or repulsive depending on the signs of charges that are interacting. The electrostatic force. So, cool fact is that the following. Point number one being made is this. Point number one being made is this. Point number one, 5.1 charges is this. Electrostatics. Statics can come in two forms. Two ways. We could have a positive charge or a negative charge. When they're opposite, they attract. However, when they are similar, like plus plus, like repulsive, so they move away. Now, a fun fact is force of gravity is always attractive. Force of gravity is always attractive. That's important. And also another fact is that charges have mass. So we can apply kinetic energy formula, which is 1/2 mv squared. Most matter is electrically neutral. As a balance of positive and negative charges ensure a relatively degree of stability. When the charges are out of balance, the system could become electrically unstable. So, turns out, most matter is electrically neutral. Most matter is electric neutral. Something you have to know is that something you can note is that the following. Most matter is electrically most matter is electrically neutral, meaning that it's a good balance of positive negatives. This is it could be most stable even materials that are normally electrically neutral can acquire a net charge as a result of friction. So when you shuffle a card, just spread out over the taller body of your body. Your hands go to, but it allows the excess charge to jump from fingers to mouth, which adds to the ground. Okay, turns out that most matter is electrically neutral. What else? What else do we know? We know that though most matter is electrically neutral, some fact about this is that most matter is electrically neutral, but can become net charged. And you may ask, how can it become net charged? It's because of friction. When you rub your, say, most matter is electrically neutral. Most matter is electrically neutral, but we learned that they could become net charged through friction. And such example is like rub when you come inside to school from like a rainy or cold snowy day. You rub your boots, rub your shoes on carpet. What happens is when you rub your shoes on carpet, you receive electrons transfer from carpet to your body. And so what can also happen afterwards is and then when you touch a doorknob, it acts as the ground because it returns electrons back to the earth. When you touch the doorknob, the ground, it's known as the ground because you return the electrons, and you get a shock sensation. Interesting. Because, okay, I see. When you touch a normal, it's known as the ground because you return the electrons to Earth. And that's why you get a shocking sensation. And so, this is one of the many examples of static charge buildup or static electricity. This is one of the many examples of static electricity. This is one of the many examples of static electricity, or or static charge buildup. There we have it. So we know that most matter is electrically neutral, but then neutral objects even become charged through a process called friction. Like when you rub your shoes on carpet, the carpet transfers electrons onto your shoes or your body, and then so you're more negative charged when you rub your feet on the carpet, but when you touch the doorknob, or known as the ground, the electrons go back to the earth, and that sensation is known as shock. This is known as static charge buildup. And this is easier in humid weathers because electric charges are separated. Charge is coulomb. Well, that's a unit of charge is coulomb. And fundamental unit of charge is 1.6 times 10 to the negative 19. So the SI unit of charge is in coulombs. SI unit, standard international unit, fundamental unit of charges. So we need to note this, that point 3 being the fundamental unit of charge is in coulombs, and 1 electron is equivalent of 1.6 times 10 to the negative 19th coulombs. 1.60. Also positive charge, even though, so this is charge, and proton, it's in positive, but electrons, it's in negative protons. Positive charge, they're both equivalent values of 1.60 times 10 to the negative 19th coulombs. Even though the magnitude take no shape of same. Note that this does not mean same mass. This does not mean same mass. Protons are more massive than electrons, if you recall the electron structure. Like mass and energy, electric charge is governed by the law of conservation. Like mass and energy, electric charge is governed by the law of conservation. And this follows the trend for energy and mass. So, like mass or energy, charge cannot be created or destroyed. Charge cannot be created or destroyed. Very important. Charge cannot be created or destroyed. Insulators and conductors vary in their ability to hold charge and transfer charge. Vary in their ability to hold charge and transfer charge. An insulator will not easily disperse charge over the surface. It will not transfer the charge to another neutral object will, especially not to another insulator. On a molecular level, two electrons and insulators tend to be closely linked with respective nuclei. By extension, most nonmetals are insulators. Experimentally, insulators serve as dielectric materials, capacitors, as well as isolating electrostatic experiments from the environment to prevent grounding. So, varied. I see. So, point 4 being made is that insulators versus conductors. We learned the following in that insulators do not spread charge easily. Insulators do not spread charge easily over surface. These could include your nonmetals on the periodic tables. Makes sense because they want more electrons at this core. It's because we have less electrons than desired, I think. Wait, is it true? Or no, maybe it's because they're more electronegative. Maybe that's why. Maybe electronegativity has to do with it. Nonmetals want to gain electrons, and so probably would not want to give away its electrons it already has. They're used to serve in dielectric. They used to serve in what? Dielectric materials and capacitors. They are used to serve in dielectric materials and capacitors. What does this mean? Interesting. And these insulators can also isolate electrostatic experiments. How? And I meant why? For scientific purposes, to prevent grounding, like the shock of the doorknob example mentioned earlier. Now, in contrast, conductors are they spread charge on surface easily. This is important character. Charge is fully with the transfer charges enough to use it circuits. And that's why they're often used in circuits, or conductors are often used in circuits or electrochemical cells. What else? They're able to transport, conductors are able to transfer charge and transport charge. Conductors are often conceptualized as nuclei surrounded by a sea of free electrons that are able to move rapidly. Only loosely associated with positive charges. So, and they are usually the metals or ionic solution like salt water. And conductors are generally metals. 5.1 demonstrates the behavior of an insulator and conductor when negative charge is placed on them. And so conductors would, in the diagram, looked like this, whereas insulators, notice on the surface, is more so clumped and not so spread out. So it looks like that. And so concept check 5.1 says, when placed 1 meter apart from one another, one will express greater acceleration, one group of electrons. So, point 1, I should say, is when placed 1 meter apart from each other, which will experience greater acceleration. Electrons. So, it seems like 1 coulombs of electrons or 1 coulombs of protons, they both have same acceleration, because we learned that 1 charge is 0.60 times 10 to the negative 19th. Wait a second. Which will experience greater acceleration? V squared mass force is equal to ma. If the force is equal, wait a second, sorry, this is wrong. I think this is wrong. This would be wrong, because 1 coulomb of electrons or 1 coulomb of protons. If they are 1 meter apart, we know that force is equal to ma. The point of this being was that to illustrate that they have different masses. Protons have a mass that's higher, so and force would be equal, I assume. They would be equal to one another because they're exerting force on each other. So then if masses, so I would say electrons have greater acceleration. Electrons would have greater acceleration too. Now, categorize the following materials as either conductors or insulators. So, conductors, actually let's go, sure, one out, conductors, insulators, blood. Hair is an insulator. Blood has lots of charges, so maybe blood. It would be a conductor. Copper is a conductor. Glass is glassy. Glass is an insulator. Iron is a conductor. Sulfuric acid is a conductor. And distilled water is an insulator. Distilled water is an insulator, I think. And 3, let's see. What's the net charge of an object with 1 coulomb of electrons and 3 moles of electrons? So, what is the net charge? What is the net charge of an object with 1 coulomb of electrons? What's the net charge of 1 coulombs of electrons and 3 moles of neutrons? One coulomb is, you said one, it's an interesting question. 3 moles of neutrons. So maybe it's just saying, is it saying 3 moles of electrons plus 3 protons? Is this saying, one coulombs of electrons? Is this saying, is this saying 1 electron? Then maybe would the net be positive 2? Let's check the answer. Concept check 5.1. Alrighty, yes. Electrons have greater acceleration. We learned this. And conductors are blood. Conductors are blood, copper, iron, sulfuric acid. Blood, copper, iron, sulfuric acid, correct. Insulators are hair, glass, distilled water. These are correct. And 3 moles of electrons. This is wrong. It's just -1, because this is not true. Because this is saying neutrons do not contribute. Neutrons do not contribute charge. Neutrons do not contribute charge. That's why. I see.